So now in this module, we are going to understand what is optimization techniques in a deep learning model and how we can work on loss functions. So optimization is a very important task in deep learning because deep learning model always learns from the surrounding or the data which is provided to it, and it improvises over the time. So the mechanism of improvisation over the time is important, otherwise it will not converge to the minimum loss, is to converge towards a minimum loss. So let's try to understand what is optimization. So in this session we are going to understand about optimization algorithms like gradient descent, batch gradient descent, stochastic gradient descent, and Adam optimizer. Then we will also learn about loss function, that is mean squared error, binary cross entropy, sparse categorical cross entropy, and sparse categorical cross entropy. Let's try to dive deeper into all these topics in detail. So optimization algorithm are, as I told you, like when we are working on a machine learning algorithm, it starts from taking data from the input layer and processing this data, uh, analyzing information or the complex trends and pattern through different level of hidden layers. Multiple neurons are there. It moves forward, the information move forwards, a output is generated. Now this output is mapped with the actual output, and it is observed that there is some kind of discrepancy, some differences there. This discrepancy is error, so we need to improvise this error. So how to improvise this error in an efficient and faster way so as to get the model effectively predicting the future unseen data. So for that we require optimization algorithm, and we have different optimization algorithms starting with gradient descent, mini batch gradient descent, and so on. Optimization algorithms are kind of crucial component in the training of deep learning model. As I told you, their primary goal is to minimize the loss function or error, thereby increasing the efficiency of the model and reducing the weights and adjusting the weights and biases of the neural network. Optimization algorithm is responsible finding out the set of weights and biases that result in the lowest possible error. Without an effective optimization algorithm, it is difficult to find an nearly like it is impossible to find a nearly equivalent model which can identify trends and the patterns in the data well. Optimization algorithms are important for several reasons. Firstly, they will help the neural network to converge to the set of weights that it is finding out, and it also helps us to converge in a reasonable time also. Secondly, they can avoid issues such as overfitting, underfitting, because at the time of training itself, it adjusted the data in order to avoid overfitting of the data with each and every epoch. Overall, optimizations are critical components of deep learning, and choosing the right method will be the best possible way. And it is also crucial to understand which would be the best way of optimizing the current learning algorithm. So we'll try to first understand the gradient descent approach. Generally, if we want to find the minimum of a function, we go by the gradient descent approach. We set the derivative to 0 and solve for the parameters. It turns out that it is impossible to obtain a closed form solution for weight and biases. Instead, we iteratively search for a minimum using a method called as gradient descent. As an analogy, we have to imagine, like we imagine yourself standing on a mountain peak and you're trying to get to the bottom of your peak. So at every step you walk into the direction of the steeper descent, since the direction is the most promising to head to lead you towards the bottom in minimum time. So gradient descent is all about finding that direction in which we have to move forward. Gradient descent also operates in the similar way. When trying to find the minimum of a function, we it starts at a random location in parameter space and then iteratively reduces the value of j until it reaches to a local minima value. At each step of the iteration, it tries to minimize or reduce, or it moves or it searches for a steepest descent where we can go across and find out the uh, the minimum error or loss function. This process is depicted for the one-dimensional case in the image. Now, the direction of the steepest ascent of a function at a certain point is given by the gradient at that particular point. Therefore, the direction of a steepest descent is given by the negative of the gradient. So now if we have a rough idea how to minimize the j, so j is the cost function, and as we are moving towards the downward direction, we are looking for a negative gradient. Here we start with the random values for weights w and biases w and b. We compute the gradients of j with respect to w and b. Take a small step along the direction of negative gradient, and we keep on doing this again and again until we converge to a local minima. So this is the entire process of gradient descent. Now there are certain versions of gradient descent. For example, we have batch gradient descent. So the pros of gradient estimates are stable, and concept needs to compute gradients over the entire training for one update. So infeasible for a very large data set and for a large neural network where there are millions of parameters to be updated. So if you are talking about batch gradient descent, it requires to analyze the data at a batch level. So initial parameter is theta, and while stopping criteria is not meeting, we will compute the gradient over n samples, and we apply the weight, and we keep on updating the weights, keep on updating the weights until we reach at a lower value of the gradient. Now batch gradient descent, we can see here with the help of a contour plot where how several step of gradient descent brings the error closer to the global minimum. We see a small step of the error gradient. Gradient descent is also known as batch gradient descent, as one of the gradient computation step requires the entire batch of the training observations going through the gradient computation process. So batch gradient descent is all about changing the weights after a certain batch is over. So we divide the data into a certain set of batches, and after all the data is getting trained, we optimize the weights. So weights are changing after the optimization and learning of all the data points. Now, on the contrary, we have stochastic gradient descent. So it is faster in convergence because it improvises at every iteration. So it keeps on iterating over each and every iteration. It keeps on improvising with each iteration. Imagine that you are trying to learn a new skill, and say if you are trying to solve 10 mathematic problems, and the teacher actually helps you out when you are completing 10 problems. So imagine you have given 10 questions to solve, and your trainer, basically your teacher or trainer or tutor, helps you out after you complete 10 questions. So batch gradient descent is all about that. So basically where we have the output or the feedback or the improvisation is done at the end of 10 or set of batch is over. Whereas when we talk about another gradient descent, where we get the improvisation at each and every problem being solved. For example, if you have 10 questions, in the previous case, when all the 10 questions were solved by you, you got the feedback. But if you get the feedback at every problem, like if you solve one problem and you get a feedback like whether you are correct or going in the wrong direction, in the second problem again you get the feedback. So this way your learning and improvisation is happening at each and every step instead of completing a certain set of batches. So this basically is a phenomenon of stochastic gradient descent, where your learning will happen at each and every step, and it keeps on improvisation. So that is why the learning basically becomes faster. So basically for you to solve 10 questions and then get a feedback, where your learning will be slow, because after a certain set of time you will get a feedback, your learning will not happen at that time. But when you are getting your learning immediately after you are solving a single problem, yeah, there your learning is fast. So stochastic gradient descent is all about getting a learning fast, where a very faster learning. And you can see the iteration over here, stochastic gradient descent. The advantages of stochastic gradient descent is computation time per update does not depend on total number of training examples. Here various in the case of batch or gradient descent, where you have to do all the training and then you get the update. No, here that is not the case. So you will get an update at a very fast pace. Instead, a parameter update is done at end of every gradient descent step on a single observation. That is the best part, and it has faster convergence than any other gradient descent, and it is suitable for very large network with millions of trainable parameters. Now, potential problems. So, gradient descent, gradient estimates that can be very noisy, as shown in the red lines. Blue is the reference lines for batch gradient descent, but when it comes to stochastic gradient descent, it is very much noisy. It can be, it can change at every instance of time. So that is why it becomes difficult to, like error never get to the global minimum, but oscillates around the global minimum. So it keeps on oscillating around the global minimum, but it doesn't reach the global minimum at all. Now, feature importance and error surface. Now, till now we assign the same learning rate to all the features. If the feature vary in importance and frequency, then it is probably not a good idea to implement this gradient descent. Like, we need to make the learning rate adaptive in nature. So we require adaptive learning rate methods. So all the features are equally important, but there are certain cases where some important features are more important than any other feature. So in such instances, we can use adaptive learning methods where it can improvise the gradient descent or the gradient value. So that is where AdaGrad takes into picture. AdaGrad basically is a method where we downscale a model parameter by square root of sum of square of all its historical values, and we keep on minimizing these values, sum of squared errors. Parameters that have large partial derivatives of the loss learning rates for them are rapidly declined. So in adaptive gradient, we rapidly decline the adaptive learning rates. AdaGrad is good when the objective is convex in nature. If we are moving towards a convex end at the bottom, AdaGrad might shrink the learning rate too aggressively. We want to keep the history in mind, so it can shrink the learning rate too aggressively. We can adapt it to perform better in non-convex settings by accumulating an exponentially decaying average of the gradient. So we can do the change in the mathematics of exponential gradient, and AdaGrad can help you out to do that. And here we can see the example as well. So while stopping criteria is not meeting, it will compute the gradient estimate function, and then it will accumulate the value of r, that is regression value of r, which is the initialization parameter, and it keeps on adding. We will compute the and update the value of delta theta and apply update again and again. So what we are doing is we are changing the learning rates and the weights accordingly at each every iteration, but the weights are getting optimized at every step for each and every parameters. So the features are getting different learning rate. Then we have RMSProp. RMSprop is a gradient descent optimization algorithm commonly used in deep learning. It adapts the learning rate based on the magnitude of the gradient, which allows for faster convergence and better optimization of data. So RMSprop computes a moving average of the gradient values, which are their squared gradients for each weights, which is then used to adjust the learning rate of for each weight. So basically here learning rate for each weight is adjusted based on the moving average of the recent grade or the weights. So the algorithm uses a decay rate hyperparameter to control the influence of previous gradients on the current learning rates. RMSprop is basically less sensitive to the choice of hyperparameters like than the other optimization algorithms, making it a popular choice for many deep learning models. Despite its benefit, RMSprop may still suffer from local minima and can be slow to converge in some cases. So it is very much useful RMSprop because RMSprop helps in optimizing the weight, and it uses the moving average method to kind of optimize the weights of a data. It is also less sensitive to choices of hyperparameter than other optimization algorithm, because that is why it has become a popular choice in the deep learning environment. In some cases, RMSprop also may converge to a local minima instead of global minima, so that can be a problem at times in RMSprop. Then we have ADAM optimizer, which is the most commonly used optimizer. So it is a popular optimization algorithm used in deep learning, and it combines the benefit of both RMSprop as well as momentum optimization. ADAM optimization computes the adaptive learning rate for each weights and based on the estimates of the first and the second moments of the gradient. The first moment represents the mean of the gradients, while the second moment represents the variance of the gradients. Now, Adam uses bias correlation terms to prevent the estimates from being biased towards zero at the beginning of the training. So, it uses a bias correction term to avoid the biasness of the data at the beginning of the training itself. The algorithm also uses hyperparameters to control the decay rates of the moment estimates and the learning rate. So, Adam optimization uses hyperparameters so as to reduce the effect of decay rates of moment estimates and the learning rate of the data.